have another hadron right next to it, another collection of 3 quarks, then the difference between where they're located is actually noticeable. And so you have an incredibly strong force that's binding the quarks together within a proton, also binding different protons together. And they call it the strong force because it's orders of magnitude stronger than any other force we know. So from there, I'm going to step into a little bit of relativity. So anyone heard of some obscure German guy called Albert Einstein? Yeah, he made a pretty big hullabaloo in the early 1900s. He came up with 2 really famous equations. One everyone knows, 2 no one knows, but the people who do know freak out about it. Can anyone tell me what the popular one is? E equals mc squared, right. The second one has to do with how space bends with gravity. We'll talk about that in the future. But essentially he said that the energy of just some particle not moving, just resting, no kinetic energy or potential energy, it has some intrinsic energy equal to its mass times the speed of light squared. And the speed of light is a constant. And he figured out that you can have particles, and if you change them into other particles, then you might lose some mass. And energy is created as a result of that. And he found that energy and mass can be interchangeable. So what happens is when you have two charges, two hadrons, there we go, close together, you have 2 protons. Let's say in helium, you have 2 protons and 2 neutrons mixed together. You would expect that the masses of those would just add up. So in atomic mass units, you have 1 proton, 1 neutron, and 1 neutron. It should be 4, right? It's actually very slightly less than 4. The reason for that being that some of the energy goes into the potential of these 2 hadrons being really close together. And you effectively have negative energy. So overall, it has lower mass. So whenever you have bits of hydrogen colliding together and fusing to create helium, energy is given off because some of the mass of all of those particles turn into kinetic energy. And I don't know if anyone knows, but C is a really big number. It's 3 times 10 to the 8th meters per second. That's how fast light travels. And even if you have a small mass, you can get a huge amount of energy from just, say, taking a proton and just getting rid of it. And so, with the strong force, that's how nuclear fusion and fission works. You change the arrangement of particles in a nucleus, which changes the mass and energy, and that change in mass creates an enormous amount of energy. I'm going to move briefly on to leptons, because that is important to understand the rest of fermions, or quarks. One thing that is important that I forgot to mention, this positive charge and negative charge, they didn't know what to call those quarks, but they figured they had to give it a name. So since it was positive or negative, they figured they'd call it up and down. So you see written U and D, that's what that means. And they assigned them charges of plus 2/3 and minus 1/3, the fundamental charge. Because back when they thought that protons and electrons were just their own thing, they were the simplest thing you could possibly have, they said, okay, this will have a charge of 1 and a charge of 1, and we'll calculate stuff in terms of that. And so they had coulombs, which was a lot of them, and they had the fundamental charge, which was the charge of 1 electron. Little did they know there were particles with even smaller units of charge. So since we didn't want to rewrite all of our units with different stuff, we just say it's plus 2/3 minus 1/3. But these are the smallest amounts of electric charge we've ever been able to find. So moving on to leptons, can anyone tell me what an electron is? What its charge is, where it's found, stuff like that? Anyone heard of an electron before? This is a simple question. Raise your hand. Shout it out. I don't care. Has a negative charge. It's found. Yeah, it's found in orbits around an atom. Does it have a big mass or a small mass relative to a proton?
Very
really small mass.
1/1840,
Tiny.
right? AMU.
Yeah, it's like 1/800th of a proton mass. Is that what we said?
No, 1840. Like
Yeah.
1840. There we go. Yeah.
So the mass of an electron is 1/1840
Yeah.
AMU. So it's tiny. But the nice thing is, because it's tiny and it still has the same charge as a proton, a small field makes it move a lot, so it's really easy to notice. So scientists like to do a lot of experiments with electrons because they're common, they're everywhere. We can use them to make screens and projectors and TVs and carry electromagnetic radiation through light waves and stuff like that. So they're convenient. And then scientists started finding electrons that didn't act like electrons. They had the same charge, but it seemed like they had masses hundreds of times bigger than you would expect. And they didn't know what was going on. They figured it had to be in the same family as the electron. And since they figured that there were these things called, what they called fermions, because it obeyed the statistics explaining how, from what we observed, how quarks behave, they figured there was another family of what they called leptons. They called them electrons and muons and tauons. Because you got increasingly heavy particles, they just call them that. So initially, in a nuclear reaction, they said that there... Yeah, I'm a little bit ahead of myself. In a nuclear reaction, when you have a neutron gives off beta radiation, gives off an electron, I'm going to erase some of this here. In fission, sometimes fission of heavy atoms, not uranium, but just larger atoms, you might have a case where it gives off what appears to be an electron, and the element itself changes. You get a neutron changing into a proton. So the way that's written is you have a neutron turning into a proton and an electron. So you have a positive proton and an electron. And that was great and all, but they had no idea why, when all of this happened, there was less mass that they could observe at the end than at the beginning. And it was actually Fermi who predicted this. He was an Italian guy. He figured that since charge is conserved, it has to have no charge. So we have a tiny particle with no mass, or with a slight mass and no charge. We're going to call that a neutrino. And they figured it was related to the electrons. They dubbed it the electron neutrino. And when they started encountering these heavier electrons, essentially the same thing as an electron, just bigger, they realized that you didn't have the same neutrinos being emitted. You would expect for just a neutrino to come off of a lepton, but there were different types of neutrinos. They couldn't figure out why. They all had different masses. So they figured there was some value that was conserved, that they call that lepton number, that has to be conserved. And so they figured it must be an anti-electron neutrino that's emitted. So looking at electric charge, you have a plus and a minus and a zero. That adds to zero. Originally you have a zero. Looking at the mass, you have all these masses equaling that masses. You looking at lepton number, you have 0, proton doesn't have a lepton number, +1 for having an electron, and -1 for your antineutrino. And they figured that must be conserved. And that's why you can have a particle where you have a muon and an anti-muon neutrino, but you don't get a muon and an electron neutrino. The reason for that being that whatever set of numbers you have beforehand, that has to be conserved. So if you have a positive, a real particle and an antiparticle,
Teachers, please
you have to have
pardon
that
the
same
interruption,
pattern.
but
After
let's
the
hear
announcements
Carol,
question.
please
Could you
come
write
to
that
the main
bigger?
Sarah,
Yeah.
Carol, to the main office. Thank you.
This is be used.
Yeah.
It's,
That good? And up here we have the nuclear reaction where a neutron decays and turns into a proton, an electron, antineutrino. And that bar above the top means it's an antineutrino. Yeah.
How do you spell muon?
Muon is M-U-O-N,
oh, not like muon.
What about the other one?
and then
Yeah, that one.
neutrino,
No, the one that starts with a T. A T.
T. Oh, and then there's also a tauon, which I'll get to later.
Oh.
T-A-V-I-O-n.
T-A-U.
Oh, okay.
T-A-U-O-N.
T-A-U-O-N.
Those are just named after Greek letters. So at this time, they figured that there were two families of electrons. They had figured out that there was the electron neutrino, the muon, and the muon neutrino. They'd also found the up and down quark. And then they looked at these reactions, and they noticed that in this case, you had some particles not appearing that with the physics they knew said they could. You didn't have an electron neutrino appearing with a muon. You didn't have a muon neutrino appearing with an electron. So they knew there was some conservation there. And then they're looking at the ways quarks interact. And they did that. They discovered that you could have different combinations of quarks, and you get different sorts of particles as a result of that. They called them hadrons, clusters of 3 quarks. And they were just experimenting with putting them in different combinations, and they found that sometimes you were getting combinations. I'm going to try to look up the specific one. Yeah. So you could have 2 particles bounce off each other and change into other particles because the quarks in one interchange the quarks in another. So they had a pi and a negative pion and a proton, and they formed a kaon and I don't know, a lambda-on. Those specific names aren't important. You do need to recognize them as referring to hadrons. And they realized that this combination always seemed to occur exactly like that, even though they didn't see any reason why quarks couldn't form together in a different way. So they figured there's some strangeness going on here. And so they said, hey, there must be some other quark, we don't know about it, let's call it a strange quark, because we don't know how to understand it. So they said, okay, we have a strange quark. They figured it behaved exactly like the up quark, but differently. It had the same charge, but a much bigger mass, which would explain the heavier particles they're encountering. And they figured there is some quantity being conserved from beginning to end of the reaction called strangeness. So kind of like here, your lepton number is conserved. So you go from 0 to +1 and -1 with your lepton. Still here, there is a strangeness value. So they figured the pion had a +1 strangeness, proton had 0, and then one of these had to have 0 and the other +1 as well to conserve that. So then they look back at the